Now, for those of you who did not see the previous presentation, and a refresher for those of you who did see it, I'm going to talk a little bit about the indexes before I start talking about how the joins are going to use them. I'm going to come back and do some of the same stuff, but instead of doing it in 20 minutes, I'm going to do it in 3 or 4. All index structures in SQL Server, with the exception of the full text index, which is out of scope, are B-tree type structures. What that means is that we are going to start with the data page. From the data page, we build an intermediate page. The intermediate pages have pointers to them from either additional intermediate pages, depending on how many we've got, or a root. The difference between the clustered and the non-clustered index is that the clustered index we think of as being physically sorted in index order. Because we can only physically sort the data one way, we can only have one clustered index. The clustered index structure looks like this. We physically have the data sorted on the data pages. For each page, we have the first entry brought up into the next index level. So the first page starts with Albert. We bring that entry into the intermediate page. The next page has a first entry of Brown. We bring that into the intermediate page, etc. on down. Once we've built the intermediate pages, if there is more than one page, we build another level. So from that first page, we bring Albert into the next page. From the next page, we bring in Jones, etc. until we're done. We keep doing this until we get down to a level that has a single page in it. That is our root level or root page. Now, how do we find something? When we want to find Joe Baker, we start at the root page. We have an index on last name. We know the last name is Baker. Baker is between Albert and Jones. We follow the Albert pointer down. Baker is between Albert and Brown. We follow the Albert pointer down. Now we're on the data page. We pick Baker up off the data page and we're done. So the cost of this particular exercise was 3 page requests. Now, because we can only physically sort the data one way, we need an additional way of bringing information back. That additional way of bringing information back is our non-clustered index. For the non-clustered index, what we find is that what we have to do is find every individual row of data. Because we need to be able to find every individual row of data, we are going to have an entry in the leaf level for each row. So 1 million data rows, 1 million entries in the leaf page. Note that in the clustered index structure, we had an entry per page. Now we have an entry per row. This implies that unless you have rows that take up the whole page, that non-clustered index structure is likely to be much larger than the clustered index structure. Much larger is generally in terms of storage. It is not hugely significant in terms of index levels, which tends to be one level deeper. After the leaf page of the non-clustered index, the index pages are put together the same way. So let's talk about how we get there from here. Let's find Amy. Amy is between Amy and George. We follow the Amy pointer down. Amy is between Amy and Bob. We follow the Amy pointer down. We're now on the leaf page. We have multiple Amy's. What do? Well, because we have multiple Amy's, we have to make a page request for each of those Amy's. 2 Amy's, 2 additional page requests. Now here's where things get interesting, particularly from a join perspective. Let's say we have 50 Amy's. If we have 50 Amy's, what's going to happen is we go from the root to the intermediate to the leaf. We probably fit 50 Amy's on a single leaf page, so we're not walking the leaf pages, but we have to make 50 separate page requests. And note these are logical page requests. They may be up in cache, but it's still 50 separate page requests to bring back all the Amy's. What if we're bringing back 50 Bakers? If we're bringing back 50 Bakers on a good day, well, we've got a 100-byte row, we got an 8K page. We may have all the Bakers on the same physical page. That's 3 page requests. Now, the cost of bringing back 50 Bakers for 3 page requests versus 50 Amy's for 53-page requests is very significant, especially as you start thinking about this in the context of a join. What if I have not names that I'm searching on, but foreign keys? Now, let's take the situation where we have a simple index header, index detail search join. If I have an invoice header ID of 20, then what I do is I say join from the header to the detail where the header ID is 20. Well, that's relatively simple, right? But here's what happens in real life. In real life, what frequently happens is the invoice detail has a primary key clustered on something like invoice detail ID, which is frequently an integer and frequently identity column. Here's the catch. When I'm bringing back 50 detail items, what I'm bringing these back on is not invoice detail ID. I'm bringing these back on the foreign key, which is the invoice header ID, which is frequently a non-clustered index rather than a clustered index. What does that mean? That means that when we are trying to perform the join for a particular invoice header, I need to make 50 page requests to bring back the 50 detail rows. Now let's think about that. What if instead I put a non-clustered index on the foreign key and I clustered on the foreign key? Non-clustered primary, cluster on the foreign. Now when I go after the index detail, I have one page and I know that my invoice detail is going to be on that same physical page. It sounds like a little bit. What does it cost you to do 50 page requests? Well, that may be 50 milliseconds. It's not a huge amount. But what if you're running invoices for 100,000 customers? What if you're a utility? You're running invoices for a couple million customers. Not only that, you're not just doing an invoice header, invoice detail join. Chances are the invoice detail is joining out to an address table where you're identifying the mailing address or the billing address or the shipping address or all of the above. You may be joining out to some types tables, rates tables, pricing tables, discount tables. It is unusual in a production environment to have a simple two-table join. So what we find is that that effect of joining on the non-clustered indexes versus a clustered index has a snowballing effect where it's not just 1 to 50, it's 1 to 50 times 50 times 50 times 50, and that's for each of the indexes that gets created. Now, back to real world. What does that mean? What that means from an indexing perspective is, well, we still want to have those indexes out there because otherwise we're doing table scans or hash joins, which cost us an immense amount of aggravation. But it does mean that we do want to go back and reevaluate our physical database design as it is affected by or as it affects our performance of the joins. I lost count years ago of the number of times I've simply changed clustered and non-clustered indexes and brought multi-hour batch jobs down to a couple minutes or less. Happens over and over and over again. So, as we start talking about the indexes, as we start talking about the joins, in the back of your head, have this information about how the indexes are working, the difference between the clustered and the non-clustered, because even though we're not going to be dealing with it a lot right now during this seminar, it's something that you absolutely must have in the back of your head as you're doing your own tuning and thinking about how the joins are happening. So, quick review, clustered versus non-clustered. The clustered tends to be 1 IO faster because it has a smaller structure. Clustered are great for ranges of data, ordered by. The non-clustered are a bit slower, take up more disk space, but are frequently the next best alternative to a table scan. Note, it says frequently the next best alternative. That does imply that there are situations where it is more expensive to use the non-clustered index than to scan the table. I'm going to go through that one again just because it's important. Let's say for the sake of argument we've got 1,000,000 rows of data, and to make the math simple we've got 80-byte rows, and so we've got 10,000 pages of data. Well, the cost of scanning 10,000 pages of data to get the 1,000,000 rows back is 10,000 page requests. We're walking a page chain that's relatively simple. Coming back to the non-clustered index structure, one of the things that we find is that if we're going after a lot of that, let's say we're going after everybody whose name is, first name starts with A through L. That represents half the data. Well, if I'm using the index structure, not only do I have to scan all those leaf pages, I'm going to end up making 500,000 page requests. Since I only have 10,000 pages, we've got a 50-to-1 ratio there that says that table scan is a lot faster. Just be aware that the more data we go after, the less useful that non-clustered index is.